Here we have discussed relative velocity by simple observations. Now we will discuss relative velocity mathematically and systematically with the help of reference frame. So reference frame, I have earlier told you, reference frame is nothing but it is a set of coordinate axis x, y, z. X, y, z coordinate axis. It's a set of these Cartesian coordinate axis system, which is called reference frame. And this frame may or may not move with a certain velocity. That is the reference frame. In physical world, you can assume any, suppose car or train as a different reference frame because they are moving with different velocities. Ground is also a reference frame. It is stationary reference frame. Car is another reference frame which is moving with other velocity. Train is moving with some other velocity, that is another reference frame. Because these frames are moving, so they will give different feeling of motion for same object from different reference frames. So what is the motion in single reference frame? So this is x, y, z coordinate axis system. In this coordinate axis system, how we define the motion of an object? Just I am talking motion from single reference frame. This is a reference frame. So as we have discussed earlier in calculus topic, how we define velocity, how we define acceleration. So that we will just recall here briefly. For single reference frame, let an object, the x, y, z coordinates of object. This object is moving in this reference frame. Hence, the x, y, z coordinates of this object. Let this object is P. As this object is moving, hence the x, y, z coordinates of this object will be function of time. Let x coordinate is given by t square, y coordinate is given by t cube, and so z coordinate is given by 3t. So coordinates of this at time t is given as t cube, t square, t cube, and 3t. This is the point which is moving in this coordinate axis system, and these coordinates are function of time because it is moving, and they are changing with time by these equations. X coordinate at time t is equal to 0, you can say at time t is equal to 0, this coordinate is 0, 0, 0. This point will be here at t is equal to 0. And at time t, its position will be given by this point, which is function of time. So let this is point A and this is point B. A at t is equal to 1 and B at t is equal to 3. At t is equal to 1 second, let it is second. At t is equal to 1 second, point is at point A. This object is at point A. And after another moment, at t is equal to 3, this object reaches from point A to point B. This object has reached from point A to point B. Coordinates we can find at different points, at both these points. So we can say for single coordinate axis system how the velocity, how the accelerations, average velocity, average accelerations are defined. that we will just discuss shortly. So from t is equal to 1 to t is equal to 3, we average in x direction, that this is point x2 comma y2 comma x2 comma y2 comma z2, and at t is equal to 1, this is point x1 comma y1 comma z1. So in this time interval 2 seconds it reaches from A to B. So V average in x direction will be x2 minus x1 divided by t2 minus t1. This is t1 and this is t2. So how the velocity of this point moving in this axis system is defined? V average velocity, because its velocity is changing with time, so it will have instantaneous velocity, different instantaneous velocity between point A and B. But between A and B, when we will find average velocity in x direction, similarly, then we will use this formula, x2 minus x1 by t2 minus t1, that you all know. So this you can easily calculate. x2 is at t is equal to 3, it will be 9 minus x1, it will be 1 divided by 3 minus 2, and this is 8. Sorry, this is 4. 4 meter per second. So average velocity of this particle in x direction is given by x2 minus x1 by divided by t2 minus t1, which you can calculate. x2 is, put t is equal to 3 in this coordinate system, so it will be 9 minus x1 is t is equal to 1, it will be 1. So that is 9 minus 1 is equal to by 3 minus 1, 4 meter per second velocity. Similarly, V average in y direction is y2 minus y1 divided by t2 minus t1. So this is y2 tq. At t is equal to 3, so we can just write the coordinates here, directly write coordinates here. T is equal to 3, this is 9, this is 27, and this is 9, and the coordinate at this point is 1, 1, 3. You can directly write coordinate with this equation. T is equal to 1, 1, 3. T is equal to 3, that is T2. Coordinates are 9, 27, 9. So y2 minus y1, that is 27 minus 1 by 3 minus 1 is equal to 26 by 2 is equal to 30 meter per second. That is the average velocity. Similarly, V average in z direction is z2 minus z1 divided by t2 minus t1. z2 is 9 minus z1 is 3 divided by 3 minus, and it is 6 by 2, that is 3 meter per second. So in single Cartesian coordinate system, we define average velocities with this. So total average velocity is Vx plus Vy plus Vz. Average velocity, these all are average velocities. So total velocity of particle will be vector sum. Total average velocity of particle will be vector sum of all these velocities, average velocities, and this can be written as in IJK term, which we have discussed, 4i plus 13j plus 3k in the form of unit vector system along xyz direction. This velocity will be 4i plus 13j plus 3k. So this is how we represent average velocities of a particle in single frame. So this average velocity, V average, you can also find by vector AB divided by delta T directly. So vector AB is displacement vector, and this displacement vector is position vector of B minus position vector of A, which we have discussed. So position vector of B is 9i plus 27j plus 9k minus position vector of A, I plus j plus 3k divided by delta T is 2, 3 minus 2. So this will be 8i plus 26j plus 6k divided by 2, and this is same. After dividing by 2 you will get this vector. So there are different methods. All methods are connected with each other. So directly average velocity you can find from this displacement divided by delta t, or average velocity from by addition of vector addition of average velocity in xyz direction. So in both cases you will get same average velocity. That you all know, I am just explaining for understanding how the velocity in single frame are defined. This was average velocity. We have learned that instantaneous velocity. Now we will understand instantaneous velocity. Instantaneous velocity in x direction at any point is given by dx over dt. We know v instantaneous, we can write it v instantaneous. Similarly, vy in y direction, instantaneous velocity is dy over dt. In z direction, instantaneous velocity is dz over dt. So just put x, y, z in these equations, we will get dx over dt is 2t, dy over dt is 3t square, dz over dt is 3t. So at time t, instantaneous velocities are given with these formulas. So you can find v instantaneous at a in x direction, instantaneous velocity. At point A, instantaneous velocity in x direction will be dx over dt at t is equal to 1. Put t is equal to 1 in this formula. 2 into 1 is equal to 2 meter per second. Similarly, the instantaneous velocity at A in y direction will be given by at point A. That means you have to put t is equal to 1. So put instantaneous velocity in y direction, t is equal to 1. 3 into 1 square is equal to 3 meter per second. At point A, instantaneous velocity in y direction is 3 meter per second. So this is how we can find instantaneous velocity at any instant of time by putting the value of time in this formula. Similarly, point B, to find point B, velocity at point B, instantaneous velocity, put t is equal to 3 in this formula. So you will get at point B, this is point A, and for point B, put t is equal to 3, 2 into 3 is equal to 6 meter. Put t is equal to 3 in y direction, 9 into 27 meter per second. V instantaneous at time t is equal to Vx plus Vy plus Vz. Instantaneous velocity in x, y, z direction. So these instantaneous velocities are dx over dt. It can be written in ijk term as I plus dy over dt, j plus dz over dt, k. So this is instantaneous velocity at time t. It can be written as dx over dt is 2t into I, dy over dt 3t square into j plus dz over dt 3k. So V instantaneous at time t is given by this equation. So instantaneous velocity at point A, you can find total instantaneous velocity is t is equal to 1. So it is 2I plus 3j plus 3k. VA instantaneous. Similarly, VB instantaneous is given by this same formula. Put t is equal to 3, hence 6I plus 9j plus 3k. This is V instantaneous at point B, whereas at point A, V instantaneous in x direction, you can say 2 meter per second, this value. V instantaneous at point A in y direction 3 meter per second. V instantaneous in z direction also 3 meter. So Vx, Vy, Vz instantaneous velocity at point A in x, y, z direction are given by these values. This can be found from here also. This is Vx, this is Vy, this is Vz. Similarly, at point B, you can find Vx instantaneous velocity in x direction. This is 6 instantaneous velocity in y direction, 9 instantaneous velocity in z direction, 3. These are Vx, Vy, Vz at point P, and these are Vx, Vy, Vz, that is instantaneous velocities at point A. So this is how we find in a single frame average velocity and instantaneous velocity in xyz direction, and instantaneous total average velocity by Vx, Vy, Vz addition, and total instantaneous velocity by addition of Vx, Vy, Vz, where these are instantaneous velocity at a particular moment. This is the method to find instantaneous velocities. Now in single frame we will find acceleration. So we know acceleration, average acceleration, A average. Average acceleration of this particle between A and B is Vb minus Va divided by T2 minus T1. If these are x components of Va, then this component will be x component of average acceleration, Vx, V. Let instantaneous velocity at B in x direction minus instantaneous velocity at A in x direction divided by total time interval is average acceleration in x direction. So this will be instantaneous velocity at B. Instantaneous velocity at B will be dx over dt at point B minus dx over dt at point A divided by t2 minus t1. So dx over dt, you know dx over dt is, we have earlier written dx over dt is 2t, dy over dt 3t square, dz over dt is 3. So at point B, dx over dt, put t is equal to 3, this is 6. In this, put t is equal to 3, this is 6, minus dx over dt at A. In this, put t is equal to 1, divided by 3 minus 1, t2 minus t1. And this is 5 by 2.5 meter per second square. That is the average acceleration in x direction. Average acceleration in x direction between point A and B is velocity at B in x direction minus velocity at A in x direction divided by t2 minus t1. At B, instantaneous velocity is given by this expression dx over dt at B, minus at A, instantaneous velocity is given by this expression at A. We have found dx over dt as 2t. Put values of t2. For B, t is equal to 3. 3 into 2, 6. Minus for A, t is equal to 1. So 1 into 2 is 1. Sorry, 1 into 2, it will be 2. 1 into 2 is 2, so it will be 4 by 2. It will be 2 meter per second. So average acceleration in x direction is for 2 meter per second square. Similarly, you can say average acceleration in y direction is vb in y direction minus va in y direction divided by t2 minus t1. Same way you can calculate average acceleration in y direction dy over dt at point B minus dy over dt at point A divided by t2 minus t1. That is, average acceleration in y direction is velocity in y direction at point B minus velocity in y direction at point A. And this is dy over dt is 3t square. For point B, t is equal to 3. Then it will be 27 minus dy over dt 3t square. Here t is equal to 1. 3 into 1, 3. Divided by 3 minus 2. And this is 24 by 2. And this is 12 meter per second square. So average acceleration in y direction is 12 meter per second square. Similarly, you can find A average in z direction is equal to dz over dt at point B minus dz over dt at point A divided by t2 minus t1. And this is dz over dt is 3. So this is for both points, it is 3 minus 3 by 2 is equal to 0. So this will be 0. This is average acceleration between point A and B in x, y, z direction. So total average acceleration between point AB is axi plus ayj plus azk. can write it like this. This we are just talking about single frame motion in single frame. So this you can write as dx over dt at point B minus dx over dt at point A divided by t2 minus t1 into I. Average acceleration A average between point A B. Similarly, plus dy over dt at point B minus dy over dt at point A divided by t2 minus t1 into j. Similarly, in k direction, dz over dt at point B minus dz over dt at point A divided by t2 minus t1 into k. So this is expression of average acceleration between point A and B, which we have calculated earlier. So this is how we understand the motion in single frame. One more thing, we can also find instantaneous acceleration. Instantaneous acceleration, we know A is equal to dv over dt. So ax is equal to dvx over dt is equal to second derivative of x coordinate, and this is second derivative of this is 2. Similarly, ay, these are all instantaneous acceleration. Earlier we were talking about average acceleration. Ay direction dvy over dt is equal to, this is t square dt square d2x over dt square, second derivative of, sorry, this is y, d2y over dx dt square, and this is 6t from this, and az, z direction instantaneous acceleration is dvz over dt square, that is dt, or you can write it d2z over dt square is equal to 0. Second derivative of 3 is 0. So this is instantaneous acceleration in x, y, z direction. So at point A, instantaneous acceleration in x direction t is equal to 1. So it is independent of 1, it is 2. Ay at point A, t is equal to 1. So it is 6. At point A, it is 0. So instantaneous acceleration in x, y, z direction at point A will be given by this. Put t is equal to 0 in this. Similarly, at point B, instantaneous acceleration in x direction 2. This is independent of time. Instantaneous acceleration in y direction at t is equal to 3 for point B. This is 18 meter per second square, and in z direction this will be 0. So instantaneous accelerations at point A and B in x directions, in y directions, in z direction are given by this expression. These are instantaneous acceleration in x, y, z direction. So total instantaneous acceleration, A instantaneous, is given by ax plus ay plus az. We all know this. These are the components in x, y, z direction, or we can say, we can write it like this: ax I plus ay j plus az k. Ax is 2i, ay is 6t, J. AZ is 0. So this is A instantaneous. So these are the methods to find acceleration, velocity, average velocity and average acceleration in single frame. So that was just short description how we define velocity and accelerations in single frame. So till now we have defined relative velocity based on our general observation, and we have defined motion in a single reference frame in terms of average velocity, instantaneous velocity, average acceleration, instantaneous acceleration, and how we find all these motions from single reference frame. Now we will describe relative velocity with the help of moving reference frames, more than one reference frame, and with one of them is moving. We will use Galilean transformation. A frame moving with constant velocity is called inertial reference frame or Newtonian frame. Newtonian frame or inertial reference frame. And why these are called inertial reference frame, that we will describe just after this discussion why it is called inertial reference frame. Till now you just remember the definition of inertial reference frame as a frame moving with constant velocity. Now we will use Galilean transformations to understand the relative velocity. So Galilean transformation, there are two reference frames. This is O. This is one reference frame having x, y, z directions. X, Y, Z coordinate system. This is one reference frame. Another reference frame this is Y dash, this is Z dash, this is X dash, and this is O dash. And this reference frame is moving with velocity v. So there are two reference frames. One is this and second is this. This reference frame is moving with velocity v relative to this reference frame. Origin of this reference frame is O dash and it has origin at O. So O dash is moving with respect to O with velocity v. So we will analyze the motion of particle from two reference frame by Galilean transformation. So let at time t is equal to 0, this O dash was overlapping with O. Both reference frame were at same position at t is equal to 0. And there is a point P having its coordinates xt, yt, zt. These are the coordinates of this point. This point is also moving and its coordinates are function of time. As we have discussed in earlier discussion, coordinates of moving point will be function of time, xt, yt, z. So these coordinates are function of time. Hence this point is moving with respect to this frame as well as this frame. So at time t is equal to 0, O was here, both reference frame were at same position. So let after time t, this frame is fixed. So relative to this frame, coordinates are at time t, coordinates x coordinate will be xt, y coordinate will be yt, z coordinate will be zt. Coordinate of this point relative to this reference frame x, y, z are xt, yt, z at time t. Similarly, coordinate of same point with respect to this reference frame we have to find. So xt is position of this point in this reference frame. In time t, this reference frame has moved distance from O to O dash. O to O dash is equal to V into t. Distance between O to O dash, this frame has moved distance because it is moving frame. In time t, this O dash distance will be Vt. So the x coordinate of this point at time t in this reference frame will be different. So we can say x dash, y dash, z dash. X dash, y dash, z dash are coordinates of same point in new reference frame, which is moving with velocity v after time t. After time t, coordinate of this point in this frame is this. So we can say the x coordinate is nothing but distance of this point along x direction. Along x direction. So we will make it more simple for our understanding purpose. X coordinate is nothing but this distance along the x direction, distance of this point along x direction. We know that is the definition of x coordinate. Similarly, y coordinate is along y direction, distance of this point along y direction from xz plane. So we can say easily, you can imagine the x coordinate in this system will be reduced by Vt distance, because this has travelled Vt distance in x direction and this point has travelled xt distance. So net distance relative to this frame is xt minus Vt. This you can easily understand. This point from t is equal to 0 to t is equal to t moves along x axis xt distance. So in this coordinate system, its x coordinate will be xt. But this frame itself has moved Vt distance in same x direction. It has moved Vt distance, so the net displacement of this point, which is relative to this reference frame, will be distance moved by this point. So for understanding purpose, you just put this point here, P xt, yt, zt. So from here you can understand this xt is after time t, distance travelled by point from 0 to here. So this is xt. This distance is xt. Hence the coordinate of this point related to this reference frame, x coordinate is xt. But this frame has moved OO dash distance, this distance. So x coordinate of this point relative to this frame will be xt minus OO dash. That is very simple to understand. This point has travelled distance xt and this reference frame has travelled distance OO dash in time t. So the x-axis distance of this point from this reference frame will be this total distance travelled by this point, that is xt, minus distance travelled by this reference frame, that is OO dash. So this will be x coordinate of this point relative to this frame. So this x coordinate is xt minus oo dash. That is very easy to understand. And this oo dash is vt. So we can say x dash is equal to xt minus vt. That is, coordinate of point x dash in new reference frame is xt minus vt. And y or z coordinate will be same. Because for understanding purpose we have assumed motion only in one direction. But please remember, these concepts are valid for motion in all directions. One direction motion we are mentioning here only for understanding purpose, to make understanding easy. Once this equation is established, that equation is vector equation, and this vector equation is valid for all directions, not only in one direction. So coordinate in xyz reference frame and coordinate in x dash y dash z dash reference frame are given by this. This transformation of coordinates from one frame to moving frame is called Galilean transformation. So you can easily understand this x dash is xt minus vt. Now velocity of this point, as we have discussed in our earlier discussion, in this reference frame velocities are dx over dt, dy over dt and dz over dt. In xyz directions, velocity of point are given by this. Dx over dt is ddt of x t, ddt of yt and ddt of zt. So these are velocities in x, y, z direction, vx, vy, vz. X, y, z direction velocities are given in this frame by these expressions. Or you can say dx over dt, dy over dt, dz over dt. Similarly, velocity in this frame, vx is equal to dx dash over dt is equal to ddt of dx dash is this xt minus vt, and this is equal to ddt of xt minus v, and this is equal to this dxt over dt is velocity in this frame. So velocity in stationary frame, you can say stationary frame minus v, and other velocities, that is vy and vz, sorry, vy in new frame is dy dash over dt and dy dash is y. So y dash and y both are equal, so it will also be dyt over dt. Similarly, dz dash over dt, in z axis direction it is dz over dt. Only in x direction, velocity in new frame is velocity in previous frame in this frame, that is dxt over dt. Dxt over dt is velocity in this frame minus v. V is the velocity of this frame. So that concept which we have discussed in our general observation, that velocity of moving frame is reduced from velocity of object when we change our frame. So that concept is valid from this argument also. In new frame, velocity is dxt over dt. This is actual velocity from normal frame minus v, that is v is the velocity of new frame. moving frame. So velocity of moving frame is reduced from velocity of object in previous frame. To analyze its velocity from moving frame, that we have discussed in our earlier discussion of relative velocity. So here also you can see velocity of moving frame has to be reduced from velocity of object, velocity of this point, to observe velocity of this point from moving frame. So the same observation of moving frame is valid here also. So till now we have discussed velocity of a moving point from moving frame and from stationary frame, and we have seen that when we observe velocity from moving frame, then we have to reduce velocity of moving frame from velocity of point to observe it from moving frame. We have seen that x, y, z, in this coordinate system it is x t, it is y t, it is z. After time t, coordinate of this point relative to this frame are given by this x, y, z. Similarly, we have seen that same coordinate of this point from this frame after time t will be given by x dash is equal to x minus dt, or you can say xt minus dt. Y dash is equal to y is equal to yt, and z dash is equal to z is equal to z. These are coordinates in this moving frame for the same point. Now we will find acceleration of this point from both frames and draw an important conclusion. Acceleration in this frame ax is d2x by dt square. As we have discussed in earlier discussion, ay is equal to d2y over dt square. After time t, instantaneous acceleration in xyz direction are given as d2z t by dt square. So in this frame, for this point, after time t, at time t, acceleration in x direction is d2xt by dt square. Acceleration in y direction is d2yt by dt square. Acceleration in z direction is d2zt by dt square. Let us find acceleration in this new frame. A dash x. Let acceleration in x direction in this new frame for this point is a dash x. It was ax, here it is a dash x. And this will be d2x dash by dt. And this is similarly ay is equal to d2y dash by dt square. Az is equal to d2z dash by dt square. Y dash is equal to y is equal to yt. d2 yt by dt square. That is same for both. Sorry, we have written here. We have to write it here. d2 yt by dt square, and this is d2zt by. This is a dash y. This is a dash z. A dash y and ay are same. d2 yt over dt square, d2 yt over dt square. A dash z, d2 zt over dt square is z d2 zt over dt. So acceleration in y and z direction for both frame are same for this point. But let us see acceleration in x direction. In this frame, acceleration is d2 xt over dt square. In this frame, put x dash is equal to x minus vt or xt minus vt. So d dt of xt minus v into t. This is v into t. This is not vt, not like xt. Xt is the x coordinate at time t, where vt is the v into t, distance traveled by this o dash distance. So this can be written as d2 by dt xt minus twice second derivative of vt. We know for vt d dt of vt is equal to v, and d2 second derivative of vt is equal to dv over dt. So it will be dv over dt. So we know this frame is moving with constant velocity. Hence dv over dt, which is acceleration of this new frame. Acceleration of this new frame is 0 because it is moving with constant velocity. So this dv over dt will be 0. So acceleration in x direction will be only d2 x over dt square, which is equal to this acceleration. So we can say that ax is equal to a dash x, ay is equal to a dash y, and az equal to a dash z. Acceleration of this point in this frame and in this frame, both are for this point in both these frame are same. Ax, ay, az, a dash x, a dash y, a dash z. So this dv over dt is 0. Hence d2x over dt square, which is d2x over dt square, same in both cases. So this draws a very important conclusion. When we observe motion of particle from a moving frame, in that case the acceleration of this particle will be same from both moving frames, whether it is moving or it is stationary. The acceleration of particle remains unchanged, whereas velocity we have seen of this particle is reduced by velocity v of moving frame, but acceleration of this particle remains unchanged in both frames. From both frames, moving frame or non-moving frame, acceleration of particle is constant. So this draws a very important conclusion why we call it a inertial frame. Even though this frame is moving with velocity v, but this frame is also inertial frame, because inertial frame name comes from Newton's first law of inertia. Newton's first law of inertia says that in the absence of any force, the motion of particle will remain unchanged. In the absence of any force, the motion of particle will remain unchanged. So this particle, motion of this particle will be same from this and this frame if no force is applied on this particle. If net force on this particle is 0, then the motion of this particle from both these reference frames will be unchanged, will not change with time, because acceleration from both frames are same, we have proved here. So if there is no force on this particle, then acceleration will be 0, and this zero acceleration will be from this frame and will be from this frame also. Both frame acceleration is same. So without force, acceleration will be zero. From both frames, acceleration will be zero. That is, particle will keep on moving if no force is applied, and this motion will be same from both frame of reference. Motion will be unchanged. From this frame, you will see if no force is applied on this particle, its motion will be same. Even though its velocity from both these particles is different. From here, it is v, it is dx over dt, and here it is dx over dt minus v. But whatever velocity we are observing from here and here, those velocity will remain constant if force is not applied on this particle. That's why this moving frame also called inertial frame, because law of inertia is applicable from a frame moving with constant velocity. Similarly, Newton's second law, Newton's third law, all law of motion, all Newton's law of motion are applicable from all inertial frames moving with constant velocities. If frame is moving with constant velocity, it is called inertial frame, and all inertial frame, Newton's law of motion will be same. That's why it is called inertial frame, because law of inertia holds true for this frame as well as for this frame. If there is no any external force in this frame, its velocity will be dx over dt minus v, that will be constant, and in this frame its velocity will be dx over dt, that will be, if no force is applied on particle. So particle will maintain its inertia in both frames without application of any force. That's why as the particle maintains its inertia, so these both frames are called inertial frame, or any frame moving with constant velocity is called inertial frame. Newton's law of motion are true for both frames, because we have seen that acceleration in both frames is constant, is same. Hence, without force, acceleration will be zero. So this transformation is called Galilean transformation. But actually, such type of transformation, XYZ coordinate system, Galileo himself has not given such type of argument, because XYZ coordinate system was not there during the time of Galileo, was not so advanced or famous or in use during the time of Galileo. So this argument was not given by Galileo in this form. But this transformation is called Galilean transformation, because this phenomena was explained by Galileo by his famous thought experiment. Galileo proposed a famous thought experiment to explain this phenomena of inertial frame, or frame moving with constant velocity. So that thought experiment of Galileo is called sailing ship experiment. Sailing ship experiment. Galileo said that suppose a ship is sailing in the ocean, along the beach, along the coast, a ship is sailing, and a person is sitting inside the deck of the ship, inside the deck, so that he cannot see the outside environment or outside view. Person is sitting inside the sailing ship, ship is moving, and person is sitting inside the ship in a deck, and he is unable to see the outside the ship. In that case, for that person, it is impossible to define whether he is moving or he is stationary. Galileo said there is no such experiment inside the ship, deck of the ship, which can prove that this ship is moving. Even though ship is moving and person is sitting inside the ship and he is unable to see outside, all windows are closed, he is unable to see outside. In that case, that person cannot determine whether his ship is moving or stationary. There is no such experiment. There is no experiment which can be carried out inside the deck of the ship for that person, by that person, which can explain that ship is moving. That's why a ship moving with constant velocity he called a inertial frame. Ship moving with constant velocity is inertial frame. Law of inertia will be applicable, and all law of Newton's law of motion will be applicable inside the ship in same way as they are applicable on the ground, shore of the ocean. The same experiments cannot be differentiated inside the moving ship and on the shore. So that was the thought experiment carried out by Galileo to explain the inertial frame, and he said that all the frames which are moving with constant velocity are inertial frames. They can be assumed in inertial frame because law of motion are same for all frames moving with constant velocities, or all frames which are inertial frames. This is also called Newtonian transformation. This is actually called this relative velocity concept by this frame of reference, Galilean transformation, is called classical physics. Newtonian, it is also called Newtonian physics or classical physics. But presently, I am just explaining you for information purpose, but that is not in your syllabus at higher secondary level. These laws of motion, relative velocity, Galilean transformation are valid only for classical physics. Only for certain cases, these laws are not general. Presently we say that we know that these laws are not general. We will mention the conditions when these laws are not applicable. First condition is this Galilean transformation, which we have said x dash is equal to x minus vt. For small velocities, this Galilean transformation is correct. But when this velocity is at relativistic velocity is close to velocity of light, in that case we find x dash by Lorentz transformation. Lorentz transformation are applicable for frame moving with velocity close to velocity of light, whereas Galilean transformation are valid for velocities, frames moving with velocity very small and not comparable with light. For Lorentz transformation, or when the velocity of moving frame is very close to velocity of light, x minus vt divided by under root 1 minus v square by c square. When the velocity of this moving frame is close to velocity of light, in that case x dash is given by this expression. There c is the velocity of light, v is the velocity of moving frame. This phenomena at relativistic speed is called length contraction. Length contraction. So this is Lorentz transformation, which is used for frames moving with velocity close to speed of light, and this is Galilean transformation, which is used for frame moving with smaller velocity and not comparable with the velocity of light. Similarly, in Galilean transformation, t dash is equal to t. In both frame, time is same. We have assumed in both frame, time is same. So in Galilean transformation, we have assumed that t dash is equal to t. That is, time in both frames are same. Delta t, which we were using in our example, t2 minus t1, that was same for both reference frames. But in Lorentz transformation, T dash is given by T minus Vx by C square under root 1 minus V square by C square. So in Lorentz transformation, T dash is not equal to T. Time in both frame also changes. T dash in moving frame is equal to T in stationary frame minus Vx divided by C square. Is V is the velocity of moving frame, C is the velocity of light. So time also changes in frame when it is moving with speed closer to light, close to light. This phenomena of time change is called time dilation. Time dilation. Time dilation and length contraction. These two phenomena are observed for frames moving with relativistic velocities, and these expressions are derived by Lorentz transformation, whereas in Galilean transformation coordinates are expressed in this by this equation, and both reference frame time is same. So in Galilean transformation, time and position is absolute, whereas in Lorentz transformation, time and position is not absolute. And this Lorentz transformation is used in theory of relativity given by Albert Einstein. So I am just explaining you that these Galilean transformations are valid only for smaller velocities. When velocity is comparable with light, then Lorentz transformations are used. So Newton's law of motion or Galilean transformation are valid in classical physics only. In relativistic physics, Lorentz transformations are used. Second thing, for very small particles also Newtonian physics is not applicable. Newtonian physics is not applicable for particles at small level like electron, neutron, proton, photon. At that level, quantum physics is applicable. So Newton's law of motion are applicable only for the mass of considerable quantity. For smaller masses, comparable with neutrons and fundamental particles, quantum physics is applied, and uncertainty principle of Heisenberg, which you have studied, is also applicable. Its position and momentum cannot be determined simultaneously at quantum level. Similarly, Newton's law of motions are also not applicable for very high mass. For very high mass like neutron stars and black holes. Neutron stars and black holes, they possess excessive mass. So in that case also, Newton's law of motion is not applicable. For black holes, general theory of relativity proposed by Einstein is applicable. Black holes are only explained with the help of general theory of relativity and not by the Newton's law of motion. So we have seen that we can conclude that classical physics or Newtonian physics has certain limitations. On velocity, it is applicable for normal velocity, not at relativistic velocity. For particle moving with velocity close to light are not governed by Newton's law of motion. They are governed by special theory of relativity. Second, Newton's law of motion is not applicable for very small masses like electron, neutron, proton. At that level, quantum theory is applicable. So fundamental particle, electron, neutron, proton and photons, we use quantum physics to explain their mechanics. Similarly, we have seen that Newtonian physics or classical physics is not applicable for very heavy masses like black holes. So black holes are explained only by general theory of relativity. So we have presently, with advancement in physics, we know that Newton's law of motion are applicable for very selective cases. But in our general life, we are living with Newton's law of motion. We are living in that range of masses of particles, velocities of particles, where Newton's law of motions are applicable. We are not dealing with the masses with electron, neutron, proton directly. Even though indirectly we are dealing with them by electricity and radio waves and all those. But in our daily lives, we are not dealing with particles at quantum level. We are not dealing with black holes. We are not moving with velocities close to light, relativistic speed. So in our general life, our life is governed by Newton's law of motion. So in reference frame also, we have proved our earlier observation that for a moving frame, when we change our frame to observe the motion of an object, then we have to reduce the velocity of moving frame from velocity of object to analyze its motion. Now we will understand this logic with a very simple example. So this is a ground and a lift is moving with velocity 2 meters per second upward. This lift is moving upward with a velocity of 2 meters per second, and when it is 1 meter, it is at 1 meter height from ground. At that time, a particle, an object, is projected upward with velocity of 8 meters per second. Gravitational field is G is equal to 10 meters per second square. So a lift is moving with velocity 2 meters per second upward. At height 1 meter from ground, when the lift is at height 1 meter from ground, an object is projected upward with a velocity of 8 meters per second. So a person sitting on the lift sees this particle, sees this object. So we have to find when this object will reach at the floor level of this lift. When this person seeing this moving object will see crossing this object is floor of the lift, that we have to find. So here this lift can be assumed as a reference frame. Lift can be assumed as a reference frame moving upward. So from ground we see that the velocity of this object is 8 meters per second. Initial velocity is 8 meters per second. So if I sit on the lift from this ground, let I have changed my position from ground to lift, which is moving, and from there I am observing this object, projected object. Then what I have to do to analyze the motion? So as I have changed my frame from ground to this moving lift, so to observe the motion of this particle, I have to, based on our observation, I have to reduce velocity of lift from velocity of this ball, or I have to add minus v velocity, which is where v is the velocity of lift. I have to add minus v velocity in this object, or I have to subtract velocity of this lift from this object to observe motion of this object from this lift. Once I subtract the velocity of lift from this object, I can assume myself sitting inside the lift and seeing the object. So from the lift, I will just subtract the motion. This motion, initial velocity v1 is 8 meter per second upward. Velocity of lift v2 is 2 meter per second upward. I have to reduce velocity vector of lift from velocity vector of ball object to observe its motion from lift. So this is velocity vector 8 meter per second for object. I have to subtract velocity of lift, that is 2 meter upward. To subtract it, I will write minus velocity vector of lift minus v2 is equal to 2 meter per second downward. So just reduce velocity vector of lift from velocity of object. So velocity vector is 2 meters per second upward. So we have taken minus v2, 2 meter per second upward, that is lift velocity. So minus v2 will be 2 meter per second downward. So net velocity vector of object is 8 minus 2, 6 meter per second upward. So from lift, I can say, once I have shifted myself to a moving frame, that is lift, I will say the initial velocity of object is 6 meter per second, because I have reduced velocity of lift from velocity of object. So for me, now the situation is that here I will say that sitting inside the lift, I will say that this object has been projected with velocity 6 meter per second upward. Here I will see upward motion of 6 meter per second instead of 8. And the position of lift is 1 meter height. So now I will apply Newton's law of motion, as I have said that Newton's law of motion can be applied from any inertial frame. All moving frame are inertial frame. So for Newton's law of motion, initial velocity v0 is 6 meter per second upward. I am applying Newton's law of motion from this frame. Hence initial velocity is 6 meter per second after reducing velocity of lift from velocity of object. G is equal to minus 10 meter per second square downward, and H is equal to 1 meter. This height of lift is 1 meter. So I have to find the time when this object will cross the floor of the lift. So we know that H is equal to ut minus half gt square from Newton's law of motion. So here H is equal to 1 is equal to u, initial velocity is 6 meter. We will take it 6, not 8, because we have shifted inside the lift from this frame. Inside the lift we have shifted, which is moving frame. So we have reduced velocity of lift from velocity of object, which is 6 meter upward. 6 minus half g is 5, 10 into t square. So this is 1 is equal to 6 minus 5 t square. ut, this is ut, here it will be t minus 6t minus 5t square. So this can be written as 5t square minus 6t plus 1 is equal to 0. So let the time t is time taken by this ball or object from ground to the floor of lift. So this can be written as 5t square minus 5t minus t plus 1 is equal to 0. This can be written as 5t t minus 1 minus 1 t minus 1 is equal to 0. And this can be written as 5t minus 1 into t minus 1 is equal to 0. So we can say t is equal to 1 by 5 and 1. So first of all, after 1 by 5 or 0.2 second, this particle will reach here, and then this will go upward, and again it will come after time 1 second. So at time 0.2 and time 1 second, it will cross the floor of the lift. There will be 2 times. First, it will cross the floor and going upward. Second, it will cross the floor and going downward. So first time, that is 0.2 second, this will cross the floor and go upward. And second time, that is 1 second, this will cross the floor and moving downward. So I have sat inside the lift and observed the motion and used the principle of moving frame. Principle of moving frame, that is that you can also find by relative velocity simple equation. Relative velocity equation you can also find. But for quick visualization, quick understanding, you can use this concept to reduce the velocity of moving frame from the velocity of object, to observe the motion of object from moving frame. When you want to observe the motion of object from moving frame, then you will sit on the moving frame, and the velocity of moving frame has to be reduced from the velocity of object in vector, with vector notations. So velocity we have reduced, and the velocity after reduction of this velocity, its velocity is 6 meter per second. And then I have found the time. So that is very simple example, only to illustrate the change of reference frame, moving reference frame with constant velocity. When we change our frame from one to another, which is moving with constant velocity relative to first frame, then we have to reduce the velocity of moving frame from velocity of object. So that was simple illustration of this moving frame.